Hello, good morning, everyone. Welcome to the latest installment of this seminar series, the Australian Geometric PDE Seminar Series. This morning, we're delighted to have Peter Olanipekun from Monash University, who will be speaking to us on the Willmore energy in 4 dimensions. Thanks, Peter.
Thank you very much, Timothy, and thanks to everyone for coming to this seminar. So this morning, I'll be talking about the Willmore energy in 4 dimensions. And so actually it's a work that I did during my PhD program. Of course, I have a paper on arXiv with Jan Bernard. It's about 52 pages. And it's the first paper you find in literature on higher Willmore energies, at least from the analytical perspective. So it's titled Regularity of 4-Dimensional Willmore type hypersurfaces. And this is the arXiv link. My goal is not to present all the details of the proof, but to just give you some of the key steps and estimates leading to the complete proof of our results. So, and of course, this is a copy of my thesis. Should there be anything that is not clear in the paper, everything is well explained in my thesis. So, so let's get started. So what's this all about? The Willmore energy is something that is well known in literature. And in this research, what I did was to look at 4-dimensional version of the Willmore energy. So the outline of my talk is as follows. First, I'll look at Willmore energy in 2 dimensions. That's well known. We'll talk about some of the notations and conventions that we adopt in this talk. And then I'll talk a bit about the Willmore energy itself and its critical point called the Willmore surfaces. And then I'll present some conservation laws. And after that, we'll move to Willmore energy in 4 dimensions and we'll talk about the problems that we find interesting in this particular research. And then I'll talk about the Willmore-Lagrange type equation associated with the 4-dimensional Willmore type energy. And then, of course, I'll present the conservation laws associated with this energy. And because we are not just interested in the computations, we want to actually see what's happening or want to understand the critical points of this energy from an analytical perspective. And the first result in this direction is the regularity result, which will be the last thing I'll talk about today. So let's see. So the notation, so we'll call sigma a closed oriented surface with no boundary. So in 2D, sigma will be a surface, but as soon as we start talking about the Willmore energy in 4D, it will be an hypersurface. Phi is going to be an immersion of sigma into R3, or if you want to talk about higher codimension, Rm, where m is greater than 3, and of course in 4 dimension it will be an immersion of a 4-dimensional hypersurface sigma. And then G will be the first fundamental form, and it will be the Gauss map, which can be defined via its Hodge star this way. So this epsilon AB here is just a Levy-Civita symbol, which you pick a minus sign anytime you exchange 2 indices. And then, of course, H is the second fundamental form. It's the derivative of our immersion. And capital H will represent the mean curvature vector. It's just the trace of the second fundamental form. Well, for us, in 2D, it's like half of the trace of the second fundamental form. In 4D, to be 1/4 of that. And then each time we can project a vector either to the normal bundle or to the tangential bundle. So by of V will be the normal projection, and pi t of V will be the tangential projection of some vectors. Okay, so with these notations, and of course with some over-repeated indices, that's just the usual Einstein convention. With all this, now let's see. So the Willmore energy itself is the integral of the square of the mean curvature, and is widely known to many people working in differential geometry. So that's been studied in literature, studied by physicists, in mechanics as well. That's been widely studied. It was first introduced by Poisson and Germain, well, independently at the beginning of the 19th century. And that was when they had a kind of competition where they had to explain the phenomenon behind a particular incident. And, so that led to the study of what we now know today to be the Willmore energy. Thanks to Willmore himself, who gave us the complete formalism of these energies. So it's just a bending energy. So there are some works that have been done on the Willmore energy. So Thomson himself, Gerard Thomson, 1924, computed the Euler-Lagrange equation for the Willmore energy. And he did it in codimension 1. And then in 1929, Blaschke and his students, they studied conformal minimal surfaces. So the Willmore, what we call the Willmore surface, minimal surfaces are just examples of it. And for him at that time, he called Willmore surfaces conformal minimal surfaces because, well, that was what that was the understanding at that time. So in 1979, Joel Werner generalized the work of Thomson in higher codimension. So he computed the Euler-Lagrange equation for the Willmore energy in higher codimension. And then in 1993, Willmore himself explored the lower bounds for the Willmore energy of a closed to orientable surface. So, and that's actually the lower bound is 4 pi. And of course, of importance is the Willmore conjecture, which was postulated by Willmore in 1965. And it goes this way, roughly, in the class of immersed tori, the Clifford torus has the minimal Willmore energy of 2 pi squared. And that was proved by Kodama and Andrew Neves in 2012, and then their result was published in Annals of Mathematics in 2014. So yeah, so now let's see. So the Willmore energy is defined this way. The vol G is just the area element. So it's the square, integral of the square of the mean curvature. And as I said, the Willmore equation is just this, is just equation 2. So when you look at this equation, you discover that it's second order in H, or fourth order equation in phi. So H is 2 derivatives of phi, and so this is 4 derivatives of phi. So it's fourth order partial differential equation, elliptic, nonlinear. And Laplace pair is the negative covariant Laplacian for the connection in the normal bundle that we obtain from the ambient scalar product in Rm. So the left-hand side of this equation 2, we'll call that the Willmore invariant. And then when you take this energy and you vary it, you get its critical point. So that critical point is called Willmore surface. So a Willmore surface is a critical point of the Willmore energy. And all these things are quite well known in literature. So now, why do we care so much about the Willmore energy? Like I said, in 1816, it was first postulated by Sophie Germain. although it wasn't called the Willmore energy at that time. It was just called the elastic energy of a thin plate. So it was studied by Sophie Germain, and that was used in explaining a particular phenomenon called the Chladni figures. Also, this energy finds useful application in conformal geometry. When you look at the works of Thomson, Shadow, Blaschke, and Willmore himself, they use this quantity called the Willmore energy law in giving meaning to some geometric quantities. And then in general relativity as well, it's the major term in what we know to be the Hawking mass. So this is the Hawking mass, and you see the Willmore energy right here appearing in this definition. So a good understanding of the Willmore energy will help us to understand the Hawking mass. So it finds application there as well. In cell biology, it's also a leading term of the F-rich energy. So yeah, so this is the Willmore energy here. So if you expand this correctly, you have integral of h squared, and Willmore energy has application in cell biology. So in mechanical elasticity and in optical design, Willmore energy is used there a lot. So that's why we care about the Willmore energy. But for us, as I said, we just want to see what this energy looks like in 4 dimensions. So, but then from an analytical perspective now, so what meaning can we give to the Willmore energy as analysts? First of all, we need to know some properties of the Willmore energy. The Willmore energy is invariant under a parameterization of domain. It's invariant under translation, under dilation, and under rotation. But not fully. The way it's defined as the integral of h squared is not really invariant under inversion. So due to Noether's theorem, we can always obtain a conserved quantity when we vary the Willmore energy on just a patch of our surface, sigma. So sigma naught is just a little portion, a little patch of the surface sigma. So you vary the Willmore energy, and then you obtain, lots of terms, some terms. And then if you track those terms nicely, you can arrange them in this form. So you have some B dot Corley W. Corley W is the Willmore invariant that I showed you earlier. So that's the left-hand side of the Willmore equation. So B dot Corley W, the dot here is usual dot product between vectors, and you have this quantity, nabla J Vj. So you vary according to this rule. So you take the Martian, you vary that, but then you split into tangential and normal component. So B is a normal vector, or B is a normal component of variation of phi. And this, of course, is the tangential component. So if you track these things correctly, you can arrange the variation of the Willmore energy in this form. So what does this tell us? So when you are at the critical point of the Willmore energy, your Corley W equals 0. That's the Willmore equation. And also, because this is a little patch, just you're on this very, very tiny surface, you have also that this quantity is conserved. And that's what you have here. So at critical point, you actually have that nabla J Vj equals Corley W equals 0. Yeah. So, but if you look at the Willmore energy, the way it's defined, you will see that as soon as phi belongs to this Sobolev space here, the Willmore energy is finite as soon as phi lies in this Sobolev space. And what that means is that 2 derivatives of phi is in L2. So your H is in L2, capital H is in L2. But then this fact, when you incorporate it into the Willmore equation, will not give you any analytical meaning. So the Willmore equation has in it 2 derivatives of capital H and then some cubic terms. So you look at the cubic term, and you see that the cubic term, these terms, right? They will not even belong to L1. So you need H to belong to L3 for you to make sense of this. So, but that's exactly what you don't have. What you have is H is in L2. So you run into a distributional problem, an analytic problem. So the question is, how do we resolve this? So in 2008, Tristan Rivia, in his paper, Analysis Aspect of Willmore Surfaces, discovered a conservation law. And he used that conservation law to give meaning to this quantity. So now this is the result. So in 2008, this result was obtained by Rivia, and Jan Bernard also obtained that in 2015 by applying Noether's theorem to the invariances of the Willmore energy. So the Euler-Lagrange equation reads, you have this equals 0, you have all this, the Willmore invariant equals 0. And Rivia said that, right, you can recast this equation as this. So you recast it in divergence form. So you have all this quantity in bracket conserved. And this is good news, because with this now you can do quite a lot of things. In fact, you can obtain the following conservation laws. So this divergence form is due to the translation invariance of the Willmore energy. So, and then due to rotation invariance, you can get this one, this equation. You can get this equation. And then because the Willmore energy is dilation invariant, you can get this equation. So L here is just some potential. It's just some quantities of potential. So you have these two equations emanating from the rotation invariance and dilation invariance of the Willmore energy, respectively. And then when you apply Poincaré lemma to these two equations, you land here. So you have the existence of some potential R and S such that these two equations hold. And then if you compute carefully this quantity, so you compute derivative of N dot derivative of R, this one, and then you multiply that with the least Levi-Civita symbol, what you have is the Laplace Beltrami of S. You have this. And there is some structure here. The structure is a Jacobian structure. So you have a Jacobian structure in these two equations. And that's good news, because now you can use Wente estimate, to bootstrap, So you obtain regularity information on this quantity S, on the quantity R, and then you update your information on L, and then before you know it, you have another equation, which we call the return equation, that allows you to transfer the regularity information that you already have of S and R to a geometric quantity like phi or H. And then you bootstrap and you are smooth. So when the estimate actually has an extra regularity information that it gives you, and then before you know it, you can prove regularity. But in 4D, the story is different, and that's the goal of this talk. So this is what we have so far in 2D, and it's well known for those who work in that area. So, but in 4D, nothing has been done. So all that we know in 4D is what the Willmore energy should look like. You find literatures in talking about the Willmore energy in 4D, trying to derive higher Willmore energies and all that, but no analytical meaning has been given to that. So our result is the first that you have in that direction. So now let's start with this discussion. So Willmore energy in 4D, what's actually the problem? So the problem will be to to know what the Willmore energy looks like in 4D. So, but before we can correctly determine what that should be, we need to have some guiding principles. So now let's look at what it is like, what it is in 2D. So in 2D, the Willmore energy is conformally invariant up to Gauss-Bonnet terms. So what do we mean by that? So you take this quantity, which we know is the Willmore energy. You can rewrite this as this one, the integral of capital H squared as 1/4 integral of H squared, plus some quantity. So this is just the Euler characteristics of the surface sigma. And then if you decide to write in terms of H naught is a trace-free second fundamental form, you have this. So because this is a topological invariance, the critical points of these three energies are the same. So studying the Willmore energy is the same as studying the critical points of the Willmore energy is the same as studying the critical points of these other two guys. So the Willmore energy is actually conformally invariant. We know that this one is conformally invariant. Well, up to Gauss-Bonnet, because actually the Willmore energy is not invariant under inversion. So not only that, when you look at the Willmore equation, the leading order operator in the Willmore equation is linear. So that's a fact that we have of the Willmore energy in 2D. So not only that, we know that minimal surfaces are critical points of the Willmore energy. I mean, when you look at the equation, so when you put in H equals 0, I mean, you discover that the equation is satisfied. So the minimal points are critical points of the Willmore energy. So that's another fact that we have. And then lastly, we know that the Willmore energy is non-negative. So if we are coming up with a 4-dimensional generalization of the Willmore energy, we would like to have these properties satisfied. We want our energy to be conformally invariant. We want our energy to have we want an energy such that the Willmore equation, its Willmore equation is linear. The leading order operator of the Willmore equation of our energy is linear. And then we want minimal surfaces to be maybe submanifolds or critical points of our energy. And then we want also that our energy should be non-negative. So let's see how far we can go. So that's the first problem, to produce a Willmore type energy that preserves these 4 properties. Yeah, so now let's talk about that. Actually, this is an interesting problem in literature, and some authors working in the area of conformal geometry, quantum physics have actually looked critically into that problem. And they found that there is a relationship between this problem and the singular Yamabe problem. So what's the singular Yamabe problem? So you have, so let me state the singular Yamabe problem. So you have a manifold of dimension n with this metric G bar. And this manifold is a smooth compact Riemannian manifold of dimension n with boundary. Sigma is an hypersurface. The singular Yamabe problem has for a defining function u for the boundary sigma of M, such that on the interior of M, the scalar curvature Rg of the metric G and G bar are related this way, via the defining function. So the metric G satisfies this relation, so satisfies Rg equals minus n into n minus 1. So that's the singular Yamabe problem. So there's a relationship between this problem and this one, which I will explain in a minute. So Leonard and Nuremberg in 1974 were the first to talk about the singular Yamabe problem. So what did they do? So they were the first to talk about the singular Yamabe problem. they computed a conformal invariant that actually obstructs the regularity of the defining function U. And then Anderson and Frederick later, so Anderson and Frederick actually were the ones that computed this conformal invariant that obstructs the smoothness of the function U. And then Rod Gover and his collaborators later discovered that this obstruction to the regularity of the boundary asymptotics for the Yamabe problem, or for the Yamabe solution, was or is a Willmore surface invariant. So they discovered that this quantity that Anderson and Frederick computed is actually the left-hand side of the Willmore equation. And then they ask if, higher dimensional generalization of the Willmore energy can be computed via obstruction to smoothness of the defining function U, in higher dimension. They did all that in 2 dimensions, but now they were asking if that could be generalized to higher dimension. And of course, they kept working, and they discovered that the answer is yes. So they got Willmore hypersurfaces invariant in higher dimension. And then they further asked if this Willmore invariant in higher dimension correspond to some Willmore energy, in higher dimension. And then in 2017, Robin Graham, and Richard wrote down this energy. So this is what came out of that research. So they have this in 4 dimensions as the 4-dimensional generalization of the Willmore energy. Of course, before then, there have been lots of research on what a higher dimensional generalization of the Willmore energy should look like. So Grosvenor and Toda, Tran in 2019, and also in 2011, actually looked at this energy. Of course, they proposed that they worked on this in 2D, but there are some researchers in this area that feel like, if h squared is the Willmore, integral of h squared is the Willmore energy, 2D, then integral of h to the power 4 should be 4-dimensional generalization of the Willmore energy. But the problem with that is that the leading order operator for the Willmore equation of this energy will be nonlinear. So it will violate one of the conditions that we have earlier agreed on. It's not only that, this was also considered when you look at this, this also fails because of the same reason. Because you clearly, when n equals 4, for instance, so when you are in 4D and n equals to 4, you discover that the Euler-Lagrange equation associated to this energy will have its leading order operator to be nonlinear. So same problem. And then the same for this. So Mundino and Ngaim in 2018 in their paper, Global Conformal Invariance of Submanifold, actually that should be section 5 of that paper, they consider this energy as a higher dimensional generalization of the Willmore energy. And but the problem with that is also that, in fact, this one does not have minimal surfaces as its critical point. So minimal surfaces are not examples of the critical points of this. So this one also fails. And of course, this one is conformally invariant. Yeah, this energy considered by Mondino is conformally invariant and also positive. Yeah, it's positive, it's conformally invariant, but does not include minimal surfaces at its critical point. This one also is, this last one is conformally invariant, but it also fails for the same reason. So now the question is, looking at that, in 2005, Guvin, in 2017, Robin Graham and Richard, and then 2021 by Zhang, they obtained a generalization of the Willmore energy in 4D. And it's precisely what I have here, equation, what I have here, this one. So this is so when you put when you project this to the when you project this to the normal bundle, then you definitely will have this in higher codimension. But the way it is now, it's in codimension 1. So so these quantities just they are defined this way. This energy is conformally invariant, but it's not bounded below. So it satisfies conditions 1, 2, 3 that we stated earlier. It satisfies this one, this condition is conformally invariant. It satisfies this condition, it satisfies this, but it's not bounded below. So to make to obtain a positive energy, one can add multiples of h naught to the power 4 and trace of h naught to the power 4 to the energy. So then you have a positive energy, but then you lose the property that h equals 0 be a solution of the Euler-Lagrange equation of this energy. So, but then, yeah, so we studied this energy which is not bounded below. It's the 4-dimensional generalization of the Willmore energy. And the first question is, so we want to see what its critical points look like, the behavior of the critical points. So first of all, we ask what conservation laws can be satisfied by the critical points of this energy. And then next, we want to find out if the critical points of this energy, if they're actually smooth. Yeah, so the first answer to this is theorem 1, which is just a computation of the Euler-Lagrange equation for that energy. So phi is an immersion of a 4-dimensional manifold sigma, and phi is Willmore type for our energy if and only if this equation 5 is satisfied. So curly W is all of this. So now we have more terms in our Willmore type invariant. And when you look at it, the leading order term is linear. So the leading order term is just 4 derivatives of h, and that's 6 derivatives of phi. So because h is 2 derivatives of phi. So what does that tell us? That tells us that this is a 6th order partial differential equation. So the question is, how do we handle this? Do we have theory? Do we have elliptic theory for 6th order partial differential equation? So how do we handle this? So the trick is to rewrite this equation in divergence form, and then from it obtain some quantities, and then have equations to second order PDE that we can actually analyze, and then from there we update the information that we have on some of these quantities. So let's see. So the first conservation law that we obtain is this one. So we have that phi, of course, is an immersion of a 4D manifold sigma, and our curly W is actually the Willmore invariant, which satisfies this equation. So so we are at the critical point here. So there is a quantity V, which is a stress energy tensor. So I mean, it's when you look at the paper, when you look at the paper, you see the complete expression of this vector. So it has a lot of terms in it. So, but we can neatly write it in this form. So F G and C are some geometric quantities. So that's our stress energy tensor. And then it satisfies this conservation law. So we have, so the first one here, the first conservation law here is due to the translation invariance of the Willmore energy. The second one is due to the dilution invariance, while the third is due to the rotation invariance. So we have this conservation law. So what do we do with this? From here, we can apply Poincaré lemma, of course. So we can recast all these equations in this form. So this is just using the language of differential forms. So we have d star of v. Well, d star is the usual co-differential operator. Of course, star is the usual star operator. So d star of v equals 0. And then d star of this one equals 0, and d star of this equals 0. So that's just recasting the previous theorem in the language of differential form. But not only that, more than that, we have the existence of two forms, L naught and L, in this space. So L naught is a two form. L is a two form as well. But at the same time, these two guys are just one. So there are two forms, but one vector. So vector value two forms. So from R4 to R5. S is a scalar, but is a two form. R naught is a two form and also a two vector. So we have the existence of these quantities, L naught, S naught, and R naught, thanks to Poincaré lemma that satisfies these equations. Yeah, so L naught and L are related by this for some U. So U here is just this space. So U is a zero form, but it's a two vector. So, and then not only that, we can compute something. So we have, so this is a big dot. So it's defined in a particular way. So it's just, it's a contraction operator. So between these two quantities. So, and of course, these two quantities are the R naught and the phi. They are not just vectors, they are also forms. So this is a one form, for instance, and this is a three form. And star of this gives you a zero form. We are in 4D. So all this is four forms. So star of that is just zero form. Same thing here, the same thing here. So this guy here is just a zero form. So we can compute this equation. G is some geometric quantity. Now that we have all this, now the next thing will be to actually use this equation to obtain regularity information on H, or phi, a geometric quantity such as H or phi. So how do we do that? So that's the last thing we'll talk about. So this is the result, the main result of the paper. So let phi be in this Sobolev space. Phi is a critical point of the energy. Phi is smooth with the estimate, with this estimate, where this is a ball now for fringes half. So we have that phi is smooth. So that's the main result. So, but in order to obtain this result, we have several preliminary results from second order partial differential equation. And then we apply that. So first of all, we say that, so we consider just a prototype of our problem. So we consider equations of this form. We can write this as this, where L is just a second order partial differential operator with coefficients defined this way. Of course, this is symmetric and it also satisfies the elliptic, uniform ellipticity conditions. So we have our first proposition, which is this one. So you have that the weak solution of this problem. So U is a weak solution of this problem, and two derivatives of U is in L2 with this estimate. So we have all these preliminary results, which we actually applied at some point to some of the geometric quantities that we have, or some of the potentials, L naught, L, S, and R, you know. So we have all that. So we have this another preliminary result. So we have quantities that we call B, quantities we call U, and then we have to prove that actually LP norm of du is controlled by LP norm of B. And then not only that, we have quantities satisfying this, and such that, of course, the U is in this Sobolev space. And then we have this estimate. So, and then another one, so if somewhere in our computations we had leftover, which we call Q, and then actually Q belonged to this space. And we were able to write Q nicely. We were able to decompose it in this form, such that the A equals 0, dB is also, this type of A is 0, d of P is 0. And then we have this estimate. So we just use this result on some of those quantities. And then, of course, we use a very powerful Bogan-Poiseuille's type result, which is this one. So so, and also we have this lemma here. I just wanted to present this result so you see. So we have this one too. So of course our energy cannot be assumed to be small. Why? Because we don't know that whether it is bounded below. So it's not bounded below. So instead, what we did was to rescale our domain so that we can obtain a ball of arbitrary center and radius with the L4 norm of the second fundamental form less than some epsilon for a very small epsilon. And then when we do that, we can actually show that the star of eta, L4 norm of this star of eta, is also small. So what is eta? Eta is just diffie wedge diffie. So first we define a quantity, this quantity derivative of L2 norm of derivative of H plus L4 norm of H, which is finite. And then we'll use this to actually bound some of our quantities. So to bound some of our quantities. So this is positive. So when you look at, so the idea is to have regularity information for H. Okay, let me write. So first of all, we have Collie W equals 0. So that's where we started from. We had Collie W equals 0. And then we're able to say that this star V, equals Collie W equals 0. And then from V, we obtained quantities such as L naught, L, S naught, and R naught, right? So the idea is to actually obtain regularity information on these quantities, V, L naught, R naught, S naught, and all that, and then see how we can update the information we have of those quantities on geometric quantities like phi or H. So when you look at the expression for V, it's in this form. So the first thing was to obtain this information, this regularity information on V. So V is in this space, and then we were able to bound it by this quantity E. So not only that, our L naught or star L naught, we were able to bound it in this space by E as well. Also, we're able to bound L in this space. So L is controlled by L naught in the same space, plus all this. So we're able to bound all this by E. So we're also able to bound, there was another quantity U in our conservation law. So we're able to bound that as well by E. And then, of course, G that I showed you earlier is of this form, and we're able to bound the U as well this way. So that leads us to obtaining this first regularity information on S naught and R naught. So both of them belong to this space. Yeah, and with this estimate. With this estimating W minus 1, 2. So, but then also we also have this one. S naught is in L2 because S naught and R naught are co-closed. So they're also in L2, and then we have this estimate as well. So V is bounded this way. So, but then the information we have on S naught, the regularity information on S naught and R naught is not sufficient to bootstrap, so it's not enough for us to bootstrap. So we have W minus 1, 2 estimates, and that's enough. It's not enough for us to bootstrap it. We are in 4D. So we need L for third estimate for us to be able to even start something nice. So, and that was a major difficulty. How were we able to resolve that? We introduced an operator, which we call L, and then with the operator L, we were able to redefine S naught. This should be S naught, S naught and R naught. So we redefine S naught to be S, some quantities, some quantity S and some quantity R. So we redefine these quantities. And then immediately, so this is the operator, we call it P. And then we created S and R from S naught and R naught. S and R have almost the same differential identity as S naught and R naught. So, and then we created these new quantities S and R. We also redefined L to be L1 this way. And then we, of course, bound L1 in W minus 1, 2. And then we obtained the S and the R. So we created S and R, as I said, and then the S and the R satisfies analogous differential identity as S naught and R naught, which is what is here. And then eventually, after doing some work, we were able to bound the S and the R in L for third. In L for third. So, and this is the bound that we have of those two quantities. And now we can bootstrap. So, but before we do that, we can bootstrap. So, but we need a return equation. So once we have irregularity information on S and R, not S naught and R naught, S and R now, we need a return equation that allows us to go from these quantities S and R naught, which we introduced, back to geometry. So, and this is the return equation. So we have a good information on this, good information on this, good information on this, and then we need an information on T, but T is precisely this. So T has H in A, nabla JH. So, so the first information that we have on that is that we're able to bound Laplace of H, delta H in L for third. And this is the bound that we have on that. And then T is bounded this way, the H is bounded in L2, and the H is bounded in L4 this way. So these two estimates above now gives this estimate, so from there we have a Moray decay, and then now we can proceed, we can use the standard argument. We define a maximal function, and then at the end we obtain that H is Lipschitz, and consequently we have that nabla phi is Lipschitz, and then we have that the phi, is in this space, and then from there we conclude, by using Lorentz space theory that phi is smooth. So so yeah, thanks. So that's it from my hand. Thank you.
Thanks for your talk. Thanks for your talk, Peter. Let's thank the speaker, everyone.
Thank you.
Does anyone have any questions they would like to ask Peter? All right, then maybe I can ask one.
Okay.
P, so once you've, my understanding of PDEs, I suppose, is that once you've established good regularity theory, you want to then construct solutions of the problem. Is that the long-term goal of this particular project? Like, what are the long-term prospects of this project, do you think?
Yeah, thanks for that question. So actually, there are lots of analysis questions that people working in this area are interested in. So this is just the first step, right? So you want to be sure that your surface or your hypersurface, in this case, is actually smooth. Is smooth, and that's what we have done. But apart from, showing that it's smooth, there are other things, especially other things that people have done for the 2D Willmore surface, right? So such things as, there's this paper of Robert Bryant where he introduced a particular formalism for studying the Willmore surface, actually via its conformal Gauss map. So, and then at some point, one wants to see if this hypersurface, Willmore type of surface for the, if one can introduce that kind of formalism to study this. So that's one thing. So not only that, one might want to see whether, sometimes you can have branch points on some of these hypersurfaces, and you want to see how you can study that as well. So there are other analysis questions that are actually of interest, but yeah, which of course I'm looking at. They are difficult, but hopefully we'll get there.
Are many solutions of this problem, of this equation, known?
Yeah, okay, so minimal surfaces are, or minimal hypersurfaces are examples of these. Are solutions of this equation. All right. So, and we know there are lots of them. There are lots of minimal hypersurfaces. So that's something, if we don't know anything at all, we know that minimal hypersurfaces are
So
examples.
how big is the gap then between the set of all minimal hypersurfaces and solutions of this problem?
How big is the what? Gap?
Yeah, the gap. What's the difference in the sets? Is that something that also people are looking at?
Well, there are also, so when you look in the paper of Robin Graham, for instance, and Zhang, they construct examples of solutions to this equation. I think Robin Graham called those anchor rings, So yeah, anchor rings. So there are examples in literature by especially authors or researchers from quantum physics, conformal geometry, who study, this energy from another perspective, So, but my perspective is just analyzing the critical points of.
Okay.
This. Yeah.
Cool. Thanks for your answers. Does anyone have any other questions for Peter?
Hi, Peter. It's Matt.
Hi. Hello, Matt. Nice to see you.
Me too. I'm just wondering if you know of a good sort of PDE reference for the div curl type regularity stuff, because it's not something that I'm that familiar with. I think a lot of people are a bit less familiar with these kind of.
Yeah, there's a book of Giaquinta, Martinati. Yeah. Yeah, so what's the title? Yeah, so there's this book of Giaquinta and Martinati where you have lots of information there.
Okay.
Yeah, so yeah, it's called, let me see. So so there is this book of Giaquinta Martinati. It's a lecture note
Okay.
Yeah, so it's called An Introduction to the Regularity Theory for Elliptic Systems, Harmonic Maps, and Minimum Graphs. And there is also this book of Eluan, Frederick Eluan. It's called Conservation Law, Moving Frames, and one other thing. So yeah, so these are good books that personally I've looked at. So yeah, maybe
Okay.
you might find them interesting.
Yeah, great. That's yeah, perfect. Thank you very much, Peter.
Yeah, thanks, Matt.
I think I found this.
Anything else from anyone?
Oh, yeah, I guess I could just ask quickly. So in your energy functional, it appears there might be, I mean, there would be some other positive terms you could throw in there potentially. Did you look at any others, and what were the obstructions of using those?
Yeah, so so when you look, okay, let me share my screen. So when you look at this one, this energy, yeah. So this is the energy we consider. So, but when you had to eat these two energies, you will get a positive energy, you know.
Sure.
But then you will lose the fact that minimal surfaces are critical points.
Yeah.
Yeah, so, and then that's what we're trying to avoid, because I mean, how would you study an energy that you don't even have examples for? So
yeah, but I was just thinking, like, so you've got those two things there with the alpha and the beta, but
yeah,
you know, you could have maybe some kind of product of positive things or something in there instead, potentially, or you know, the trace of the square then squared, or some other things that give rise to positive stuff, but they may not be geometrically as good. I don't know.
well, well, maybe, yeah, maybe.
I'm
so,
just suggesting, because I'm sure you must have tried, you probably tried various different things, and like what might the obstructions have been. Yeah.
yeah, so I tried lots of energies actually. So I tried, you know, computing. I computed a lot. So, but what I had in mind was that whatever I come up with at least must satisfy these conditions, these first three at least.
Yeah.
So some of them did not
That
satisfy.
probably rules.
So,
yeah, that
so,
rules out various combinations, I guess. Yeah.
yeah, yeah.
Okay. Thank you.
Yeah, you're welcome.
All right, we might leave it there then. Thanks all for your questions, and we'll thank Peter again for a fun talk.
Yeah, thanks. Thank you, everyone.
All right, I'll stop recording now.
Bye, everyone.